So okay, so well, again, hello to everybody. For me, my personal experience of spectroscopy at the very beginning, it was more than 15 years ago now. And on the left, you can see on my C8 telescope, it was an instrument, a very basic instrument made of wood, and with just a grating, diffraction grating with a photo lens in front of in back of the telescope. And this was enough to do the kind of spectra that you can see on the right. So it's not exactly with this instrument, but this is the same time, the same period, and this is roughly the kind of observation that we were able to do. And when you see this spectra on the right, you have three different spectra. The top one, I think, if I remember properly, it is Vega. So in any case, it is a hot star, and you can see a very smooth profile, a very wonderful rainbow. And you can see some deep lines at a few positions, and only few lines. The other star below, in the middle here, I think it is Arcturus, or in any case, it is a cool star, a red star. And you can see a lot of absorption lines, and this is totally different. And the bottom one is, well, it is a BE star, so we will come back on that later. But the idea is that in this case, where you do have some absorption at some position here in a what I would call a normal star, you can see some emission. You can see a small blue, light blue emission, and there is another one here, which is almost not visible in the red. And this is a BE star. And this is just to show that in spectroscopy, even with a very basic instrument, very simple thing, you can see a huge difference between different stars. Okay. On the bottom left corner, you have a picture that was taken in, I think it was in 2003, at La Rochelle, where we had a wonderful meeting organized by professionals about the collaboration between professional and amateurs in astronomy. And for a lot of us, it was really the beginning of the story. And you can see here Christian Buhl, who was at this moment starting to work and to discuss about the potential design of what would become later the LARES-3. Okay, so for us, this meeting is really something, an important moment for in our lives, because we did start this adventure. I have also a few examples of spectra. So again, this is a very, very old pictures that I take here. And well, this one is more recent, but well, anyway, it was in 2015, so it's not really recent. But anyway, here are different kind of spectra that you can see with a given instrument. Here is a spectrum of the sun. So it's a high resolution spectrum. Sorry, oops. It's a high resolution spectrum, so it means that sorry, again, the high resolution, because you only see a part of the green part of the spectrum, okay, green and blue on the left, and you can see a lot of lines, okay. And the second one is a spectrum of a comet, and then you can see the center, the core of the comet, and nucleus in the middle, and you can see the effect of the tail of the comet, which is a kind of nebulae with these strange shapes. The next one is a star spectrum. So in this case, this is just an horizontal line. And the next one is a neon lamp. In this case, you have vertical lines. And well, the idea of all spectra is at the entrance, at the input of the spectroscope, most of the time you have a slit which makes possible to isolate a very small fringe of light. And this is this fringe of light that is spread out by the instrument. So depending on the kind of light you put in this slit, you may have something which is wide like this. So in this case, we looked at the sky, and then you have some light that goes, that illuminates the whole slit, and then you can see the spectrum across all the slit. In the case of a comet, it's a little bit different because you have nucleus, which is point-like in the slit, but you also have the nebulae, which takes some width in the slit. When you observe a star is just a very simple point. And when you put this point in the slit, the result is that you don't see the spectrum on the above and below the star. But you may see it if you would put some light. But because the star is point-like, then you only see a line horizontally. Okay, and in this case, when you are taking a neon lamp, for example, or any calibration lamp, then you have some emissions at some specific wavelengths, and because you are illuminating this slit with a wide illumination, again, the light comes in the whole slit, and you have this effect that the lines are occupying the whole height of the image. Okay, so even if it is almost the same kind of instruments, so some are high resolution and some are low resolution, but this is the same instrument that can give all these spectra. The last one in the bottom is the Jupiter spectrum, and in this case you can see that you have some inclination of some lights here, some lines, absorption lines here. The wide, very wide here is inclinated with a specific angle, and some other lines have an inclination with a different angle. And this is a wonderful picture, in fact, because it gives an information of about the rotation of Jupiter. Okay, so we'll talk again about that later. I think that Olivier will talk about that. All this is the kind of images that you can see when you are walking close to the telescope and you are taking the images. So they are the real raw images that you can see. But usually when you want to do science or you want to do any analysis of your spectrum, it's much better to convert this, for instance, this star spectrum, in this kind of profile. And in this case, you do have the wavelengths, which is the horizontal axis, and you have a relative intensity vertically. Okay, so and then you have this profile that gives so this is the data we work on. Okay, so the raw data is that, but based on the raw data, we are processing this data. This is a quite complex data processing, but we make it as much automatic as possible. And then once everything is under control, this is something which is very fast. But the idea is to provide your result in this kind of format. Okay, in this case, this is a spectrum of Vega, and Vega is probably the first star to observe, because this is really the absolute reference star in the sky. Okay, now I can show you a few examples of different stars that was made. So it was these pictures were made in 2015. So a few years ago, and the different spectra that I'm showing to you now have been made exactly with the same instrument, so which is in LP600 with behind a C8 telescope, the C8 that you have seen on the picture before, and with this camera and so on. So this is exactly the same setup, and all the spectra has been taken during the same night in the same conditions, there to show you that how different can be the different spectra. So this is the Arcturus spectrum. This is a cool star, and the general shape is increasing with the wavelengths. and you can see a lot of lines, okay, a lot of lines all along the spectrum. And here we are covering the whole visible spectrum from roughly from 4,000 angstroms to 7,000 angstroms, which is, generally speaking, this is the visible range, okay, or this is a 400 nanometers to 700 nanometers. Okay, so this is one star. This is Vega, so this, I've already shown this before. In the same conditions, and you can see that the exposure time was 7 times 1 second, so it's very short exposure because it is bright stars, of course. And if you do that with the same exposure time, you have a totally different profile, okay? So in this case, the profile is decreasing with the wavelengths, and it is very smooth. And you can see some deep, very deep absorption lines, okay? So it is totally different. Now, if you look, for instance, at Gamma Cassiope, Gamma Cassiope, you know, the W shape of the Cassiope constellation. The Gamma Cassiope is in the middle of the W, so it's very easy to find in the sky. And when you look at this star, you will see something like that. So instead of, again, this is a hot star, so the general profile is decreasing. But instead of having absorption lines, you will have huge emission lines at the same position of the absorption for Vega, for instance. Okay, and this is very strange, and this is very impressive. Gamma Cas is a BE star, and this is why these stars are so impressive and so interesting to observe. And on top of that, a lot of BE stars are changing from one day to the other. And so this is not the case for Gamma Cassiope. If we observe Gamma Cassiope today, we'll probably have exactly the same shape as this one. Well, the difference will be very small, but there are a lot of BE stars that are changing from one night to the other, or even some are periodic and some are totally random. Okay, another star, YCVN, this is a carbon star. And if you look at the carbon star with a telescope, with your naked eye in a telescope, you will see that these stars are very, very red. Okay, totally, they are beautiful. They are totally red, and we can see that, which is, you have a lot of energy in the red part of the spectrum, and you have almost no energy in the blue part. So this is why it is so red. And when you see the general profile, it's just amazing to see these jumps in the light. And so there are complex stars, and I will not go in detail. Well, I wouldn't be able to explain exactly why we do have this profile. What I can see as a beginner is really that this is a totally different profile to the previous one. Again, another star, TCRB. This is a symbiotic star, I think, and this is also something which is very variable over the time. And again, you can see a huge emission. Always at the same wavelengths, you know. So, and these wavelengths are interesting because, in fact, these are the wavelengths of the hydrogen lines. So these wavelengths are the signature of the hydrogen in the spectrum. And so these lines over the time will change, and these emissions that we call outbursts are very interesting to follow and to track to understand what happens in this star. Okay, now, so for me, it was really my first experience when I started in spectroscopy, is that even with a very basic instrument, so the LP600 is not so basic, but the very first spectra that we took with some friends showed that from one star to the other, the differences are huge. And this is very impressive to see that there are a lot of objects in the sky, and each has a very specific signature. And of course, you can understand that this is the beginning of the story in spectroscopy, because when you try to understand why there are so many differences, then it opened the doors to the astrophysics. And step by step, you will understand a lot of things. And how do we have been able to understand how stars works, how galaxy works, how the cosmos works, and so on. And really, we can do a lot of things with that. And of course, we need to understand that, and we are curious, you know, and we want to better understand what happened. What do I have to look at in a spectrum? This is a very common question when we see that. And in few words, we will look at the general profile of the stars. So is it increasing or decreasing with the wavelengths? And you also have to look at the absorption and emission lines. So what are their position? What are their shape? Are they at the right place, or are they a little bit shifted by the Doppler effect? So this is the kind of information that we look at in a spectrum, and it will give a lot of informations about the physics that happens in the stars, or in the objects, not only the stars, but in the object that we observe. Okay, it's very important also to see why, to understand why there are so many differences between the objects. And also, if you look at several stars of the same spectral types, they will be very similar. But if you look randomly to 20 stars in the sky, you'll have a lot of differences, but you'll have a lot of similarities from some stars to some others. And this is the beginning of the game to understand how it works. Okay, you also have to when you start in spectroscopy, you also have to understand how works a spectroscope, because it's so with the spectroscope, we do see something that our eye is not able to see. Okay, our eye is able to see the difference in colors, but in spectroscopy, we have much more information than only the colors. So really, the spectroscope will see something that your eye cannot see. And then it's important to understand how it works. So it's purely optics. It's quite simple, but we have to understand it to be sure that we are properly managing our observations. Okay. Also, when you will start in spectroscopy, you will have to collect you'll have to have a spectroscope, of course, a telescope, a mount, a CCD camera, and even several CCD cameras to do the tracking of the star. So this is an important point to see, okay, so what kind of elements do I need to do spectroscopy? And this is something that we can help you to go in and to go in. Oh, no. Okay, so that we can help you to start when you want to observe. We also have a question that comes very quickly after searching in observations: is it serious? So are we really observing something which is real, or how can we be sure that it's not just artifacts? You know, and this is important to say how serious it is, and the best way to do that is to redo this observation with different setups, different observers, and compare our results, and then you will see that what I showed you is real. And also, when asked the question, is it really serious? A lot of people think, and at the beginning, I thought personally that well, the professional astronomers has already observed everything in the sky, so there is nothing else to discover. And this is totally false. Okay, you know, we still, well, of course, we already know a lot of things about the universe, the stars, the galaxies, and so on. But there is still a lot of things that are ununderstood, and that we need to still observe to better understand how it works in the sky. Okay, so it's really this adventure is really not finished. It is on the way, so, and we can. We can use all the experience of all our predecessors, which are so numerous, and it's very interesting. But we really have still a lot of things to do. Why these observations are fascinating? The first point for me is that in fact, the starlight that we observe, and when I'm talking about star, it can be star or nebulae or galaxies or any kind of object, but the stars are already most of the sources of the light in the sky. And a starlight reaches us unaltered even after a journey of thousands and millions of years. Okay, this is just incredible. This light has a so long journey, and they arrive to us with a lot of information about the source and also about all what happens during the journey. And this is just fascinating for me. And this is really, we're very happy, because if the light of the stars were changed during this journey, we couldn't do anything. Okay, but because this is unaltered, then we can really do science and understand step by step how works the star, the universe, and so on. This light contains a lot of information about chemics, about physics, about the movements by the Doppler effect. You know, if the light source is moving toward us, then the spectrum is shifted towards the blue part of the spectrum. And if the object is moving away, then in this case, the spectrum will be shifted toward the red. And this is the redshift of the very well-known redshift of the galaxies. This Doppler effect allows us to measure some movements. And of course, in the universe, there is a lot of movements that we can observe. Okay. Also, something which is very interesting is that the whole astrophysics is concerned by this spectroscopy. We can talk about solar system. We can talk about exoplanets, which is a very active field of research currently. We can talk about stellar physics, which is one of the key of the universe, about nebulae, about galaxies, which is also another very active area these days, and about the cosmos, which is an even bigger scale in the universe. And all these domains are interested by the spectroscopy. So really, the spectroscopy gives us a unique way to reach the stars. And of course, we'll never go directly to the stars, at least for some time. And the spectroscopy is the tool that allows us to switch from astronomy to astrophysics and then understand the physics of the sky. Okay, very quickly, in a spectrum, you have two axes. The first one is the axis in angstroms or in nanometers. So this is the wavelengths. So this is the color of the spectrum, and in this axis you have a lot of information. So for instance, when you see these lines, it's important to measure at which wavelengths they are to identify them. Okay, and especially we cannot identify a single line, but we can identify a pattern of line like this. Okay, all these lines are working together, and these are the hydrogen lines, and we have to know their wavelengths to be sure that this is the hydrogen. And also, if they are a little bit shifted, then it means that the star has a movement. Okay, so through the Doppler effect. So we in this case, we have to have a very accurate calibration, wavelength calibration, to make sure that we can measure the velocities. We also are interested in this case to the line profiles. Okay, so very quickly, if the activity of the star, so the rotation of the thermal activity of the star, then the lines, the absorption lines or even emission lines will be widened, and then when you measure the width of the lines, you'll have an information about what happened in the star. So we are looking at the line profiles, and we also are looking to some chemical elements. In this case, in Vega, we only see the hydrogen lines. It does not mean that there is only hydrogen in these stars, but this is only the hydrogen which is excited in this star. Okay. On the other axis, which is the intensity of the relative intensity, we are talking about the general profile. So again, we're talking about the general profile, and especially in this profile, we have the rough idea of the temperature, of the surface temperature of the star. And we are also looking at the abundances. So, I mean, we can see the depth and the relative depth of each lines, and we can compare the relative depths of different chemical elements, and then have an idea of the chemical composition of the star. Okay. By experience, we can see three types of observation in the amateur world. So the first one is really to do some personal studies. If you just want to redo some observation, if you don't believe me and you want to do your own observation to make sure that you can observe what I showed you at the beginning, this is really a first step and an important step, of course. Don't believe me, please do it yourself. So this is the first step. Another activity which is very important in astronomy in general, but even more with the spectroscopy, is to do some education at any level. So it can be for schools or universities and associations and so on. But you know that the astronomy is a fantastic way to learn science, and spectroscopy is even better because you can do mechanics, you can do computing science, you can do measurement science, you can do electronics, you can do software, you can do observations and so on. And this is very interesting to teach young people or less young people. Okay, and the third step, or the third type of observation, is when you want to give a contribution to the science. And you can really, as an amateur today, you can contribute to the knowledge and to the human knowledge about the universe. And for me, this is a deep motivation, of course. And just beware that you can do it. This is really important, that we all together organize our observation. And in this case, we can really give some knowledge to the humanity. Very that's simple like this. Okay, I think that if you want to jump into spectroscopy, there will be three steps. The first one is okay, how it works. What do I need? And you'll take some time to collect all the different elements, the telescope, the mount, the camera, the spectroscope, all the cable, all the adapter rings. Am I able to focus my spectrum, my telescope, and so on? So this is really a kind of do-it-yourself step, and you have to collect everything and make things working together. It can be quite frustrating, but for sure we can help you in this part, because we know quite well how it works now. The second step is to talk about techniques, and especially how do I do some measurement, because we are doing some physical measurement. And so don't be afraid, but it is quite simple at the end. But you'll have to ask yourself, okay, I've been able to do a first spectrum. Is it okay? Is it good? How can I improve it? what makes that it can be better than it is, and when I compare my spectrum to others, what are there some differences, how can I improve myself, and so on. So in this part we are really talking about techniques, and it's important to understand what we are doing to make sure that the observation we are doing is very significative and very real, in fact. Okay, and there is a lot of knowledge here that we can share, and this is a very important part and interesting part. And the third step, sorry, is then to do a lot of science. This is important when the instrument is under control, when you have the process to, the process to process your data quickly and efficiently and so on, then you can forget the instrument and use it to collect the light from the stars, and then you enter in the world of science. Really, my experience says that when you are doing astrophotography, for instance, this is a never-ending story. So you always have to do better. It's never finished to improve your pictures. When you are doing spectroscopy, you have to learn some technical stuff. You have to collect a lot of several elements. But one day you can say, okay, I know how it works. I know my instruments, I know how to control my instrument, and I know how to process to do a good observation. And then starting from this point, you can really focus on the science, and and that's it. And from this moment, you will, how can I do that? You will never go back, in fact, because you know how to process a spectrum. This is important. And of course, this when you are talking about science, this is when it really becomes interesting, because we are talking about the universe. We are trying to understand the universe, and it's much more important than just trying to make a telescope working. Okay, a very quick image also. This is a general principle of the spectroscope. So at the input, you have the slit. I talked about that before, just to isolate a fringe of light, a very thin part of the light. We send this light toward a collimator lens that transform the light beam from the slit in a parallel beam. We send this light to a dispersion element, which is a prism or a grating. And this prism or grating, this dispersion element has has the specificity to split deviate the light rays with different angles depending on the wavelengths. Okay, so for instance, the blue rays will go all in the same direction, but they will go with a different direction from the red rays. Okay, and this is the job of this element. Of course, this is the core of the spectroscope. And after that, you just have to put back another not a collimator, but an objective lens that will do the reverse of the collimator. It will refocus the different rays to the sensor, but because of these different angles, then you will have at the end different positions of the rays on the sensor depending on the wavelengths. Okay, and this is what makes the spectrum exactly. If we do that, if I compare to if I compare this structure to the LP600, for instance, we have exactly this shape. So we have a slit at the input of the instrument. We have a collimator lens, which is a doublet in this case. We have a dispersion element, which is a grism. A grism is a combination of prism and grating. And the advantage is that it deviates the grating, the prism, in few words, will spread out the light, and the grating will deviate it back to the axis. So we will have a general shape which is on the axis of the instrument. This is thanks to this combination of prism and grating. Okay, and after that, we have the objective lens and we have the sensor. In the case of the LP600, this whole instrument is only few centimeters long. Okay, it's a very small device, but we have exactly this shape and it works perfectly. Okay, now I want to give you a few secrets. So maybe if you have to keep one slide in my presentation, it's probably this one. When you start doing spectroscopy, first start with bright targets. This is obvious, but really a lot of technical details means that you will improve your instrument. But at the beginning, it's important you can do your first spectrum, and to do it, I really recommend that you go for bright targets. If you do that, even if the instrument is not optimal, even if not everything is under control, you will have a spectrum, and then you will be able to start improving. Okay, so start with bright targets. This is very important. The second point is really take the time to control the telescope independently from the spectroscope. You have to master the telescope and you have to master the spectroscope on a table before assembling the two instruments. These are two independent instruments, and it's important to not discover everything together. Okay, this is really a very important key for me. After that, when we are talking about science, just remember that the light is made, is manufactured, is built. Either there are two ways, in fact. It is done either by excitation of the atoms or by heating some material, a very high temperature, of course. So these are the two ways of making some light. So if you see some light somewhere, it means that either you have an excitation process or a very high temperature somewhere. Okay. On the contrary, when you look at an absorption line in a spectrum, it means that this is the signature of something along the path, the light path. Okay, so it can be dust, it can be gas, it can be somewhere, it can be inside the star itself. It can be the envelope or disk around the star. It can be some interstellar medium, we usually call it ISM. It can be also in the Earth's atmosphere or even in the instrument. So you may have some light that had a journey of millions of years, and only the last few centimeters just changed drastically the result. So when you have an absorption line, something happens along the path of the light. Okay, also keep in mind that the Doppler effect, just to have an idea of the scale, the Doppler effect means that if something is moving at 50 kilometers per second, which is fast on the Earth, but which is very common in the space or in the universe, the spectrum will be shifted by roughly 1 angstrom. Okay, so 1 angstrom, 50 kilometers per second. Just to give you an idea, the rotation of the Earth on its orbit around the Sun is something like 30 kilometers. So it means that if you observe a given star with a 6 months difference, so at one moment in the year when you are going toward the star, and 6 months later when you are moving away from this star, you will see a difference of 60 kilometers. And 60 kilometers means it will be 1.2 angstroms roughly. And 1.2 angstroms can be measured with our instruments. So it means that if you do it seriously, carefully, you can measure the rotation of the Earth around the Sun. And again, please don't believe me, do it yourself. Okay. Also, an important point before starting for real spectroscopy, a good observation is when you have put a maximum of photons into the slit. Okay, this is really the key. When you think about your instrument, when you select the instrument, when you tune it and think, you can really have an influence on the result. But when the night arrives, the instrument is frozen and you cannot do a lot of things anymore. And you can just put the star light into the slit. And during this observation, you just have to put as many photons as possible into the slit. So it means that you have to take care of the focusing of your telescope. You have to take care of the tracking of the star, putting exactly the target in the middle of the slit and so on. And this is really the difference between a good and a bad observation with a given instrument. This is how did you take care of putting all the photons into the slit. Okay, another important point, sorry, there is an accent, a French accent in my presentation. Please immediately process the data, or process your data as soon as possible, because you know that if you do the observation and you say, okay, so I will process my data tomorrow or the day after, most of the time we never do it. So we try to have the software that is simple enough to do it very quickly, but it's important to process your data very quickly. And again, this is probably the most important secret, that there is still a universe to discover. So don't believe that everything has been done already. This is not true. And we really need you to contribute and participate to this observation, to this step. Okay, so I think I've almost finished. Yeah, at the beginning, I showed you the setup and the instruments I used at the very beginning of my own history in spectroscopy. And now these are a few pictures. So where I am today, and I'm very lucky because I do have my observatory and I have this shelter, on the automatic shelter with the RC8 telescope and 10 microns mount, which is just wonderful. And I'm using a UVX spectroscope, which is also an incredible instrument. And all these instruments can be remotely controlled from home. So this shelter is in my backyard at a few meters from where I'm talking to you right now. And this is, of course, a big change, but compared to 15 years ago, but in fact, the size is almost the same, and the principles are the same also. Today, and when I look at what are we doing and what will be, what will we have tomorrow in spectroscopy, we have to consider that we have incredible tools today. We have the new CMOS sensors. We have wonderful computing tools. We have the astrometry, the plate solving, which changes totally the way to find a star in the sky. We have the 3D printing that allows us to make really new instruments for a very simple way and in a cheap way, and it really changes the game. And so we have incredible tools today, and we still have a lot of things in front of us, wonderful things. We also have a very dynamic community, the very international, worldwide community, and this is just wonderful. So we have a lot of projects, of collaborative projects, and you can just participate to whatever you want, and even create a new project if you want. And really, we have a wonderful team all around the world. And we have some new observations to come. We probably have something to invent. And I like to say that, for instance, Christian Brill just started and just proposed a few days or weeks ago to observe all together with the StarX instrument, which is the dedicated, which is the change of the Solex to observe the stars. And where the Solex is made to observe the sun. And he proposed to observe as a starter the SS433, which is a microquasar, a very interesting target, but really the idea is to observe it all together and have a common observation. This is really something important. today the professional astronomers focus a lot of budgets to huge instruments. So it means that there is less and less small instruments in the professional world. And when amateur astronomers are working together, we really offer a new kind of instrument to the community. And this is something I think we still have to do some wonderful things together, not only by adding the observing time, but also by working together and even observing the same target at the same time all together and collect collect all together the raw data to simulate a bigger instrument. So this is really something that we can do all together, and this is just wonderful. Okay, well, you probably know that I wrote a book a few years ago, and it gives a lot of technical details to, it covers a lot of points that I've discussed today. And you'll find here a lot of information to how to start, how it works, and so on. Okay, that's it. Thank you for your patience. And well, if you have any questions, please ask, or we can also switch to Olivier's presentation. Oh, and I see that Olivier, you sent you did start the
yes,
quiz. Wonderful.
Yes,
thank you,
and all participants will answer to the question. So we have a full participation. It's very great. So hello.
There is a lot of real beginners, which is very good, and I was really thinking to you with this presentation. Wonderful. Okay, you can switch, Olivier, and I will look at the.
So hello to everybody. Just do my presentation. I do my presentation with some example of what we can do in spectroscopy and with amateur instruments, not professional instruments. So some, let's say, some very small telescope or refractor. Just to have a panel of what we can do in spectroscopy with amateur instrument. First, I would like to. I would like to show you this image of M45, the open cluster in the Pleiad cluster. And just to show you that the power of the spectroscopy. When you take an image of M45, you just will see some colors, blue colors, so hot stars. And you will see that some stars are brighter than others, but that's all. But if you take a spectrum of each of these stars, you can see that all the spectra are very different from each other. So for me, it represents the powerful of the spectroscopy. And on this profile, I just show you a H alpha profile. You will see that we have emission line, you have absorption line, you have double absorption line. So all these spectra are very different from each other. So for me, it's very, this is the next dimension we can have with the spectroscopy than a simple image. We just, in the simple image, we just see colors or object, but we don't see all the information that the light produced and came to us. So what we can do in spectroscopy, so we can study the spectral signature of an object to determine its nature. For example, is it a hot star? Is it a cool star? Is it a planetary nebula? Is it a symbiotic star or a comet? Or you can have a different signature depending the object you take in spectroscopy. You can measure, of course, the speeds, redshift, rotation of a star, rotation of a galaxy, the stellar wind, temperature, matter density, shock wave. In fact, in a pulsating star, I can show you some example of shock in the atmosphere of the stars. The presence of a cloud of gas around the star, the evolution of an object over time, because in spectroscopy we can see evolution of a star, even if the magnitude of the star stay stable. We can see that there are some great evolution of some kind of star. We can detect more or one or more companions around star with a multi-star system. We can detect exoplanets, but it's very difficult with amateur telescope and amateur spectroscope. But we can see it's possible to detect some exoplanets. We can, of course, measure magnetic field with adding a polarizing system in the front of the spectroscope. And you can perform also spectroimaging of spectrolography with the sun, and the spectroimaging, for example, for planetary nebula. So what kind of spectrograph we can use by amateur? So I just show you 6, but there are many more spectrographs all around the world. But this is the 6 spectrograph is mostly used by amateur. The first of one is a star analyzer, but the star analyzer have no slit, so sometimes it's difficult to take a precise part of a non-punctual object. It's very difficult to take some spectra with this kind of spectrograph with no slit. But you have the LP 600, you have the LISA, you have the LIRIS-3, you have, of course, the StarX or SolX. This is a 3D printing spectrograph, very low cost. Shellac sells optical kits, and you have all the 3D print parts on the Christian Buell website, and you can build your own SolX by yourself with a 3D printer. And you have, of course, the UVEX with UVEX because you can go far in the near infrared or far in the near UV with this spectrograph. It's very great because you have a range about 340 nanometers to up than 1000 nanometers. So you cover all the visible domain and a part of the near infrared and in near UV part of the spectrum. So the universal spectrograph does not exist. It depends what you want to take to study. So you have to adapt the spectrograph according to the target you want to observe, and the optic on what we want to measure, see, or imaging with the spectrograph. And in fact, we have two great parts of the spectroscopy. You have the low resolution with low dispersion grating. So you can take with this kind of spectrograph very low magnitude object. And of course, you which allow to have the whole spectrum in the visible domain in one time. On the other, you have high resolution, and with high resolution, it's for humulus object because you have more dispersion, so you disperse light on a bigger surface. So with a small telescope, you can't, for example, take a spectrum of a target of magnitude 14 with a high resolution spectroscope. Or maybe you have a bigger telescope, 1 meter or 2 meter, so maybe it's possible, but with 8-inch telescope, it's not possible to reach magnitude 14 with in high resolution. But you have more detail in typical wavelength line, so you can study more precisely the evolution of typical line like H alpha or O3 or helium 2. So you can have very precise view of a line in high resolution. So, for example, if you want to study the spectral type, the signature of an object, for example, if you have on the spectral, you can see 2 stars. One is blue and the other is lightly red. So one, you can see when you see this image that the blue star is hot and the red star is more cooler. And if you take the spectrum of these 2 stars, you can have this result. So the red one is a cooler star. It's a K type star, and with many lines. You can see there are many lines, and it's very difficult to identify all the lines because there are many iron lines. There are many lines, so it's very difficult to say that the line is iron, this line is hydrogen. But in the other hand, the blue star, it's a A5 stars, and you can see there are just hydrogen line, and you can see here there are other line, but it's atmospheric or telluric line, so it's not the line coming from the stars. So it's more when the star is very hot, you have just few line, just hydrogen or sometimes helium line, but no more line like iron or other line. So it's very simple. It's a very simple spectrum. So here is some. I just put 6 different type of spectrum. From several objects. You can have the spectrum of Vega. Vega, it's a hot star of type A. You see the continuum grow up in the blue, so it means that the star is hot. And you have a BO star here. The only difference between Vega and its BO star that you can see here, the small emission of H alpha line. And sometimes on other BO star, you can have H beta or H gamma in emission, or all other Balmer line in emission. You can see, you can have also a cool star. So the continuum go up in the red part of the spectrum. You can have symbiotic stars. Symbiotic star is, in fact, there are two spectra in the same spectrum. You can see a cool star here with this like a sour profile, which is titan oxide. And you will have also some emission line from the other companion of this star. This is a more hot star, like a B star, but a very massive star, who take matter from the cooler star. So this is a symbiotic system. We have a matter transformed from a star to the other stars. You have also a comet spectrum, and in comet spectrum you have molecular bands of CN, NH2, or so on. You have a molecular spectrum, and you can identify like this the structure of the core of the comet with this kind of spectrum. And you can do, of course, a planetary nebula spectra with some emission line. You have, in fact, a continuum close to nothing, in fact, very straight continuum. And you have many emission line, like a nitrogen line, hydrogen line, oxygen line, or so on. So if we talk about BA stars, we can see that the BA star, we have hydrogen line in emission, but the emission look different depending the way you look of the star. If you are in the A case, you can see the BA star from the top, so you will see the stars, and you will see the disk of matter or the cloud turning around the stars. And you will see, in fact, this kind of profile with a single peak of emission. If you are in the case B, you will see the star in an angle of 45 degrees, and you will see, in fact, two peaks. A peak coming from us in the blue part, shift on the blue part, and another peak coming from the red part. So that's why you will see, in fact, the cloud or the disk in a different way. So you will see, in this case, two peaks. And if you look at the last thing, if you look the star like the C type, you will see two peaks. So in fact, you can see when you have a profile, you can see, okay, I see the stars like this or like this. You can say what the angle of your vision you have of the star from the Earth. And BA stars, some BA stars are very stable. François talked about Gamma Cassiope. Gamma Cassiope, it's very bright BA star, and it's very stable because if you take a spectrum of Gamma Cas, you always seen H-alpha line in emission. But other BA star, like this one, sometimes the disk is present around the star, and sometimes the disk is disappear completely. So for this example, in June 2015, I take a spectrum of this BA star. This is a black profile, and you will see there are no emission. It's a classical absorption profile with no emission. And 1 year after, I take the same spectrum of the same star, and now the profile, the H-alpha profile, is an emission. So that's why the best database was created to gather all spectrum from BA stars to see, in fact, the evolution of the BA star from outburst on a classical B star profile. And this project was made by Coraline Henner, who was an astrophysician from the Paris Observatory in France. And this database was created in, I think, in 2005. And there are more than 2,000 BA stars inside this database. And at this time, more than 1,000 don't have any spectrum in this database. So there are a lot of work for amateur to take spectra from this more than 1,000 stars and put the spectrum into this database. And today, we have in this database, we have more than 355 spectra in this database. So it's very great. And all great measure, about 90% of this spectra was made by amateur. There are about 1,054 amateurs who observe BA stars and put their spectra into this database all around the world. And you have special tools. If you, for example, if this night you want to observe with a spectrograph, but you don't know what kind of biostar you want to observe. And you have the RS beam tools. You have the website address on the below of my screen. And you have the list of all biostar. And with you can choose the biostar you want to observe. If you will see a code color when it's green, no more observation are needed because the period observation is about 1 year. So in the database we need 1 spectrum per year. But we have other biostar, like for example V442 Andromeda, who need about 1 spectrum per day. So it's a very intense observation of this star because V442 Andromeda have a great evolution each day. So you will see the profile of this star change every day. Another typical study what we can do in amateur spectroscopy, it's a binary spectroscopic stars like MISAR. And if you take, for example, 1 spectrum per night during 42 days, you will have this kind of, here it's a representative of spectrum, like we say in dynamic 2D dynamic spectrum. In fact, this is made by this software, and you can put all your spectrum day by day, and just to do this kind of graph to show, in fact, the two stars crossing each other during the time. And you will find the period of the star here about 20 days of the period of the revolution of the two companions behind the center of the mass. Here is the evolution of the same data, the evolution, but with the graph of on H alpha line. And you will see that sometimes the H alpha line is all in absorption, and sometimes is doubling. They have a doubling peak inside the absorption line. And so this is the evolution of the star during 42 days. Another another star is RRL. It's a pulsating star whose period is about 13.5 hours. And it's very amazing to see this star because you will see the HFI line come in emission only some about 30 minutes to 1 hour per cycle. So it's very short moment that we can see the emission line in emission. And sometimes during cycle, there are cycles that are more strong than other. And when there's very strong emission, HFL emission line, you can see sometime the helium-1 line in emission during all just 10 or to 30 minutes. That's very short time that we can see this star in emission at this wavelength. And also you can have the sodium line splitting during the same time. You will see at the normal component of the star, the D1 and D2 line, so sodium line, are just one, and after they are doubling here, shifting, splitting the line in 2 parts. So it's great to observe this star, but because it's just one night, you can catch all the evolution of these stars. Another star very interesting is DBW Wool. This is a pulsating star with a short period about less than 5 hours. So the same thing, you take one spectrum, for example, each 10 minutes, and you put all the spectrum in the order of you take the spectrum, and you will see, for example, but there are other lines that move also. The helium-1 line, you can see 2 shocks. In fact, in the helium light, so show in fact the shock in the atmosphere of the stars. So there are one shock. The first shock is here, and the second shock happened here in the middle of the period. So it's very impressive to see that. Of course, you need to have a high-resolution spectrograph to do that. For example, a LIRIS-3 or a StarX equipped with a 2,400 groove per millimeter rating. But you can see this kind of shock very easy with a high-resolution spectrograph. Other measurements that we can do with high-resolution spectrograph is to measure a stellar wind, for example, from P-Cygnus stars. And so P-Cygnus stars, it's in fact you have a great H-alpha, but other Balmer line also are in emission. But you have here the H-alpha line is in emission, but very, very high emission of H-alpha line, but follow in the blue by a small absorption part of the same element. So hydrogen is in emission here and in absorption here. And if you take this part, this part is in fact shifted in the blue part. So when the signal is shifted in the blue, that means that the signal, the matter, come in our direction. So you can measure in the simple way with the rest line of H-alpha here. You subtract the value of the blue part of H-alpha shift in the blue, and you apply the Doppler effect, the Doppler equation, and you have the Z coefficient of Doppler equation, and you multiply the Z coefficient by the light velocity, and you obtain the velocity of the wind velocity of P-Cygnus. So with, of course, a high-resolution spectrograph. Other thing you can do with high resolution is when we have a bright nova like Nova Del in 2013, who explodes in August. It's very bright because I think the magnitude is about 6. So with high resolution spectrograph, you can have this kind of spectrum. And you can, in the first night of the apparition of this the spectra, I have take all the night on the same target and take one spectrum each 10 minutes. So I can see, in fact, in one night, the evolution of the star. You will see here the evolution of the nova during only the first night from August 14 to 15. And you can, of course, calculate the velocity of the ejecta of the nova. And you will see here at the beginning of the night, the ejecta is this value in kilometer per second. And at the end of the night, we lose about 30 kilometers per second of velocity during only one night. And if we take this time, the evolution on 1 month, here it's H beta, but it's the same on H alpha, you will see here the great evolution of this nova just in 1 month. And if you compare the stars in August 2013 and in August 2015, so the evolution in 2 years, you will see that the profile is very different. We start with the P-Cygnus profile at the beginning because the ejecta go very fast and around the stars who explode. And then 2 years after, and we are, in fact, we call this the nebula phase. So this nova is now very stable, but sometime, maybe in the future, the explosion come again, and the cycle come at the same time. So this is the signature of a recurrent nova. It's just only 2 years. Another domain with who amateur can do a very, very good job. It's a confirmation of planetary nebula. Many amateurs in imaging find some objects who are not identified clearly. So they are very, very small. Sometimes they are very small objects. So they have a name. For example, here you have a name of KN66 because KN is just the first letter of the name of the man who discovered this object. And the only way to say what is it is to do a spectrum of this target. So here is an example of this target. It's donc KN66, and we take this profile with, of course, we work in low resolution in this case. So you have to use an LP600, a LISA, or a StarX with a low resolution grating like 300 groove per millimeter. And you take a spectrum like this, and this signature is typical from a planetary nebula spectrum. So KN66 is a planetary nebula. This program, this is a program collaboration, and the first time this collaboration take place, in fact, in 2003 at the CNRS. This is a research center, a French research center in France. We have a congress with amateur and professional, and we meet Agnes Hacker, who work at the Strasbourg Observatory, and this is a specialist of planetary nebula. And we work together since 2003 to take a spectra from several targets to have confirmation or not for planetary nebula. And at this date, in 2022, we have more than 1,000 PN candidates, and just only 125 PN have been confirmed by spectroscopy with amateur astronomer. And at this date, more than 600 don't have any spectra in the database. So now it's Quentin Parker from Hong Kong University who take the PI leader in this collaboration. And sometimes we have very strange object. Of course, yes, I forget to say that we have a special website dedicated to planetary nebula confirmation. This is planetarynebula.net. And if you go to this web page, you have all information about, you have the list of the candidates, you have the tools to know how to take a spectrum of these very, very faint targets. You have all information. Don't worry. I show you here the page in French, but you can have this page in English, of course. So sometimes we have some strange objects. For example, this candidate, we have a very noisy continuum, but you have a very great H-alpha line in emission. So we don't know exactly what kind of object we have. So we send an email to Professor Steve Shaw, who work in Pisa University in Italy, and Professor Steve Shaw work a lot with amateur. And we have this kind of answer. So it's very great for us, for amateur, to have this kind of answer. He'll explain what we have, like of a spectrum, and have some hypotheses about maybe it could be a star. So well, this is an answer. We have other spectra, very typical of spectra. For example, some target. You will see, in fact, KN66. This is a real planetary nebula. On the up, you have APP1 spectrum, and you will see that the line of H alpha or O3 are shifted in the red part of the spectrum. So this is not PN spectral signature. And if we measure the redshift of each line we can see in this spectrum, you will see that, in fact, this is an unlisted active core galaxy. With the Doppler equation, we can measure the redshift, measure the velocity of this galaxy, and of course, with the Hubble constant, we can have the distance of this galaxy. So it's very easy to do this, of course, in low resolution spectroscopy with an LP, LISA, or a StarX with a small dispersion grating. And we do a publication with some friend we have discovered with this PN confirmation program for newly discovered H2 galaxy. We has no reference. It's not so now. We have reference about this new galaxy. Another surprising PN candidate, it's a case of PA30. PA30 was an object found by an American amateur astronomer who find just a dot on the survey plate of astronomical professional survey, and find a small dot that there are no reference. So amateur take this is Pascal Ledieu who take this spectrum with an LP 600 on his Newton 8-inch open at 5. He takes this spectrum. First, if he says that, oh, it's very noisy, and I think the signal in the blue part of the spectrum is not a signal, it's noise. And he asked two other amateurs to take the spectrum of this same target with to confirm or not the possibility of this great emission line in the blue part of the spectrum. And the two other amateurs find exactly the same result. So he say, okay, it's not a noise. And he sends the spectrum to Quentin Parker in Hong Kong. And in fact, this is a great observation, because this spectrum was in fact the supernova who exploded in 1181 years. So this is the origin of this supernova, found because of an alert launched by an amateur. Because in fact the professionals have the result in their database, but they say that there are no more study of this star because they have only the part in the visible domain. So if you see the spectrum here, in fact the professional have a spectrograph who go to 400 nanometers to more than 800 nanometers, but they don't see this great emission line in the blue part of the spectrum. So they say there are nothing to see on this spectrum, and we put it in the database, but no work on this spectrum, no more work on this spectrum. But it's a very great observation, because there are not many supernova at this time during more than 2,000 years. So it's a very great discovery, in fact, made by an amateur just with an LP600 on an 8-inch Newton telescope. And of course, amateur can have a good, really good job to maintain all the database in the SIMBAD portal. And you have, for example, two planetary nebula here. One is confirmed like a planetary nebula. It's LDU 13. And the other, it's always as a state of a possible planetary nebula. And maybe need to have a spectrum to confirm the nature of this target. These targets are very, very, very faint, about magnitude 17 to 20. It's very faint, but what we have the chance, in fact, that if it's a planetary nebula, we have a wavelength in emission, we have a line in emission, so it's more easy to have a signal if we have a line in emission than a line in absorption. Another faint object, this time taken with a StarX, so StarX made by Christian Bill. And here, Christian Bill take this spectrum of UM402 quasar. It's a quasar of magnitude 17, so not very bright quasar. And you will see the quasar, it's just a small dot here. And of course, he put the quasar into the slit here. And it obtained with 16 exposure of 15 minutes each, this profile. And in fact, this emission line, it's a hydrogen Lyman alpha line, who normally was at in the near UV in the far UV part of the spectrum. So with the redshift, it can be visible now on the spectrum with just a StarX. Another thing we can do in spectroscopy is to do measurement to rotation measurement of a line. For example, if you see there are a group, a cluster of fish, and the fish turn each other, and you will find fish coming toward us, and other fish move away from us. So the fish moving away from us, they are redshift. So they are if the fish sang, you will heard a sound will go deeper, deeper sound, and the fish coming toward us, a higher sound, so is blue shift for the image. And in the case of Jupiter, you can see that if you put the slit here in Jupiter, in the equatorial part of Jupiter, you will see, in fact, the movement of Jupiter coming toward us, and the planet will move away from us. And in fact, the line is tilt or inclined. This is the line of Jupiter, which is tilted, in fact, and is the straight line here. It's in fact the atmospheric line. So at the same spectrum, you will have a straight line, atmospheric line, and inclined or tilted line here of Jupiter. And this way, you can measure the velocity, the rotation velocity of Jupiter, just to measure the difference velocity by Doppler effect here and here. Another measurement we can do this time with a low resolution spectrograph. It's a galaxy rotation measurement. Here it's a galaxy, Cepheid galaxy. I take a Cepheid galaxy because it's more easy to find a redshift on rotation with emission line than with absorption line. So I put the galaxy in the slit of the here it's an LP 600. I use this LP remotely from Chile, and I put this galaxy, the core and the arm in the slit. And I obtain this spectrum. You will see the core here, about magnitude 10, and the arm of the galaxy, very more fainter, about magnitude 16.5. And you have the right arm here and the left arm here. So when you process the spectrum, you obtain this spectrum with the core of the galaxy, with, of course, emission line of H alpha, nitrogen, sulfur line here, the double sulfur line. You have here H beta, a small emission in O3 here. And if you take the spectrum only on H alpha from the right arms and the left arm, you will see that the two arms are shifted. And if you have measure the wavelength here and the wavelength here, you have the velocity, rotation velocity of this galaxy at this point. And I precise here at this point because, in fact, this is not the real diameter of the galaxy. The diameter of the galaxy is more larger because here you have the radio image of this same galaxy superimposed with the visible image I show you in my spectrograph slit. So you will see the visible image. Oh, sorry. The visible image is very teeny. Instead of the whole galaxy, I think the whole galaxy is 3 times bigger than the galaxy we saw in the visible domain. And so we have here the Dopplergram. It's not me, it's a professional Dopplergram you can see a velocity on the redshift, the core here. It's about a redshift of 1,300 kilometers per second. And you will see different velocity from the left arm on the right arm. But you see the visible domain from me, I just take velocity of the arms here about here, but you will see here that in fact the velocity is very bigger than I can measure on my spectrum. Another spectrum, it's a quasar of very distant quasar, about 12 billion light years. So the quasar is, this is the auto-guiding field of the spectrograph. Here it's a LISA spectrograph with a C14 Celestron 40-inch telescope. And here is the quasar. We put it in the slit here. And because it's very faint, we auto-guide on this star, more brighter star present in the field of view of the auto-guiding camera. And in fact, we have here, it's very noisy, of course. I take 12 exposure of 15 minutes each. But I see here the Lyman H alpha, Lyman alpha line, who normally was at 1,200 angstrom, and now shift at more than 5,000 angstrom because of the redshift of this quasar. So you can measure it very easily with this kind of spectrum. Another interesting target, it's the Cepher Galaxy Type 1, this one, magnitude 15, taken with LISA. And in fact, this spectrum shows two types of line. A broad line of hydrogen line. You can see on the broad line here with width with a large emission line. Oh, sorry. And you have a very fine or narrow line here of 3, for example, where it's very narrow. So, in fact, in this galaxy, the narrow line are coming from the arms of the quasar, of the galaxy, and the broad line are coming from a disk who are rotate close to the black hole at the center of this galaxy. So, with the width of this line, you can measure the rotational velocity of the disk, accretion disk, just around the black hole. And another typical spectrum we can do in a spectroscopy, it's when we have a supernova appear in a galaxy. So here I'm very lucky because in October I just take a picture of this galaxy just to measure this redshift, and I put the core of the galaxy into the slit. But 18 days after, there are supernova who appear in the same galaxy here, and I have take this spectrum, and this is the spectrum. Just with 12-inch telescope on an LPC100 taken in remote from Chile. And this spectrum, this is also a contribution for professional work. I put this spectrum into the transient name server database. And in this database, there are two other spectra taken with NTT, so a very big telescope on the Salt in South Africa. But me, I just have a 12-inch telescope, so my spectrum is very noisy compared to the NTT or the Salt telescope. I finished my presentation for stellar object with SS433. This is a campaign launched by Christian Bull, like François said in the presentation. So this is a microquasar. Microquasar, it's a very particular target and very rare target. There are only, I think, there are only 5 or 6, I think, microquasar in our galaxy. So microquasar, if you take a spectrum of this microquasar, you obtain a very high H-alpha line in emission. And we have secondary H-alpha line in emission shifted in the blue and shifted in the red. So here, a spectrum taken in 2012, you can see here the blue companion of the H-alpha line, because it depends, in fact, of the orientation of the accretion disk around the black hole. Because, in fact, microquasar, what is it? It's a black hole, a small black hole, about 8 solar mass, who have a companion, giant A star, who turn around this black hole. And the black hole, in fact, take matter from this star and inhale matter, and you will see here this is not an artist animation. This is a view taken in radio wavelength animation of what the quasar, what the black hole inhale of material from the stars orbiting the black hole. So it's very interesting to take spectrum of this target, because the evolution is very big from one day to another. Here it's a comparison between 2015 to 2022, but you can see here that sometimes the blue part of H-alpha is shifted. Here the black line is taken in 2015. You will see that the blue shift H-alpha line is close to the main H-alpha line, but sometimes there are a big shift of this H-alpha line in the blue, and the same in the red part of the spectrum. And in fact, this means that the signature of when the matter coming through, in fact, the black hole. And here a comparison with Christian Will, we take this spectrum close to the same time, but with two different spectrographs, a Solex for Christian, an LP600 for me, and at two one is taken in France and south of France, On the other, I take this spectrum from Chile nearly at the same time. So we obtain exactly the same spectrum. So it's very good result. Shows that amateur can produce a good repeatable data with two different setup located at two different places. And this is the monitorings about over several nights taken by Christian, and you will see in the blue part of the spectrum, the H alpha shifted in the blue, the evolution, and the evolution is very. I think there are one spectrum per days, and you will see the evolution of the spectrum each day. So it's a very strange object to observe. And what kind of phenomena you can study? We can study the system precession. So like the Earth, that the movement of the black hole turn around its own axis. You have inhalation of matter by the black hole. You have sometimes eclipse from the giant stars on the black hole. And you have random phenomena. Sometimes the black hole inhale more matter than other time. So there are many things to do with this kind of target. And in 2014, with some amateur at the OHP Spectro party, Stéphane Charbonnel, me, and Jamie Dlin, an American astronomer, we do a spectra. We do during all the night with Lisa some spectra for this quasar, and we have found, in fact, that each 10 minutes the quasar, the profile of the spectrum profile change very fast. So with Steve Shore, with the professional who are in the field with us during the OHP Spectro party, during the night, this telegram, astronomer telegram, to say that we have seen some evolution on this macro quasar. So I think many study can be done on this micro quasar. Another way but it's very extreme for amateur, is to study measuring low radial velocity with exoplanet in spectroscopy. So here you have the Doppler shift measurement made by Christian Bill with C11, so very small telescope, on a Varese spectrograph. A Varese spectrograph, it's only a grating, high dispersion grating, and a small refractor like a Takahashi, I think Takahashi 85 millimeter. And it takes several points of measurements during time. But here you can see here the excess is not in kilometer per second but in meter by second. So it's he can have this precision because he use CCF, a cross correlation function, to measure the shift not only on one line but on one 100 or more line. So he have a precious measurement of each line. And with this, he can find the period of the exoplanet. So you will see here the calculation by ISIS. He find a period about 4.22 days, and the real period is 4.23 days. So it's very close to the real period. And the semi-amplitude of the star velocity, it's 56 meters per second, and Christian find 52.5 meters per second. So it's very great result comparing to in fact, the comparison, the graph here, it's a comparison between the first detection made by Michel Mayer in 1995 is now have the Nobel Prize in 2019, and the result taken by Christian Bill. And you will find that the two curves are very similar, but not use the same telescope, because Michel Mayor have this result with 2-meter telescope, and Christian Bill only with a C11 telescope. So we can do, of course, spectral imaging with a spectrograph. Here, this is how to scan M57 planetary nebula with here it's a LISA. You can see here the slit, and in fact, we put the edge of M57 close to the edge, the slit, and move the guiding star in Y-axis to move then about all the night to, in fact, scan all the whole object. So it takes time, because for each exposure we need about 30 to 40 minutes. But we can obtain, at the end, this kind of image. So we can choose, in fact, the wavelength we can have the image. So here we can have an image with nitrogen, hydrogen, or oxygen, and you have this image in color. And you can take what you want, helium-2, neon line, or nitrogen line, to have this kind of image. But you can have you can do some calculation with this kind of data, and you can measure electron density of planetary nebula. And upstairs, up here, you have professional measurement, and here on the back, on the bottom, you have amateur measurement taken with an LP 600. So, of course, it's more noisy than the professional image, but you can do this kind of observation, and you can calculating temperature, density. I not explain all the calcul you can do with this kind of images, but we have on the Sheglac website, we have an article. We explain all what we can do, all we can do with the planetary nebula spectrum. Another way to use a spectrograph is to do a spectroheliography. Of course, the best at this time, the best way to do spectroheliography is to use a Solex with 2,400 groove per millimeter grating. But you can do the same thing with a Lyris 3 with the same grating. You can obtain the same result. So this is the scan taken by Christian Bill of the Sun in the H-alpha line. And you can take, of course, protuberance of the Sun. And you have here the animation taken by Valérie Denou on the border of the Sun, and you have the evolution minutes by minutes of the protuberance close to the border of the Sun. Always taken with the Solex spectrograph. You can do also a magnetogram of the Sun. Here on the left, you have an image of a classical visible image that you can see in a telescope with just a solar filter. And then with Solex, you can have a magnetogram image who show, in fact, the part of the Sun very active in magnetism, in fact. And you can have also a Dopplergram of a sunspot. Blue part, this is the part of the image coming to us, and the red part it's part of the image go in the other direction. So you can do many things with the Solex. And here for my last slide, this is just a list of some program collaboration in spectroscopy. Just the main collaboration. There are many collaboration all around the world, but here is some the main collaboration in spectroscopy with comet, supernova, symbiotic star, novae, planetary nebula, biostar. You can follow all this actuality on maybe some alert of some typical object to study or to take to have a spectrum on the ARAS forum. This is the address of this website, and we have also a list dedicated to the alert launched by professional. It's a Spectral list with the address here. And more to come, we are in discussion with LESIA. LESIA is a laboratory of in Paris Observatory in spectrography. And in fact, they want to add in their database spectrograph image taken by amateur. Just because sometime in Paris the weather was not good, so they can't observe the sun, so they have some hole in the database and want to add other spectra coming from other observer to have a continuous observation of the sun in their database. For my last slide, I have two reference books to propose to you. It's about the first one, you know it because François says that in this presentation. This is a very great book of François about spectroscopy, and it's very complete, and you have answer to all your questions. And the second book is Astronomical Spectrography for Amateur. This is book is following the program meeting of Olivier in 2003 in France. And in fact, this is the beginning of the collaboration between amateur and professional with several subjects like planetary nebula, biostars, comet. We start with this book. So now I thank you for your attention, and if you have any question, I will be happy to answer it. Thank you.
Thank you so much, Olivier. Wonderful. Well, we didn't have a lot of questions in the chat. So now, if anybody want to open the mic or ask a question in the chat, as you prefer, we can take a few questions. Please give your comments, ask your questions. I know it's always difficult to be the first one. Nobody?
Okay,
Yeah.
I want to thank you for this event. It was wonderful to listen you and your experience. Nowadays I am reading your book. This is really excellent, and I'm underlying all the most important parts, and I recommend to everyone. I'm a real beginner, and I want to ask. I have a Lisa with I will use it with a 10-inch Newtonian. I want to learn how will in your book you explain it, but I need a more practical answer. How will I see this exact star on the slit? I guess I need a camera with to plate solve the image, or I don't know, a pointing camera, find the star and put it on the slit, and then take the spectra. But I mean, does it depend on the focal length of the telescope or camera? How will I choose a practical solution for pointing camera and the lens or scope in front of it?
Well, this is, I will try to answer. I know that at the beginning, it is impressive to say, hey, how can I point at a star? And how can I be sure that this is the right star? I think this is your question, right?
Yeah.
So well, I may have two different answers. A few years ago on my side, I did use in fact, I had an old mount and very imprecise mount. And in fact, I did have a parallel camera to use it as a pointing star with a very short lens in front of it to have several degrees of field of view in the sky to be sure where I am in the sky. And I did measure exactly when I point at one given star, I know where it is in the pointing field. You know what I mean?
Yeah.
So I did use two different devices to be sure that I was pointing at the right star. And I used this wide field camera to select exactly to position, to put properly the telescope position to this star. And now I knew that when I was close enough to the reticle in this camera, I was sure that the star was in my guiding camera. And then I was able to put it in the slit and so on. So it was a few years ago. Now I do have a wonderful mount, which is a 10 micron one, which is much more precise. And now I'm using a UVX with the improved slit, which has a better reflection. And so we can see more stars in the field. The slit is bigger also, so I have a bigger field of view. And now with these instruments, I can quite easily do some plate solving directly in the guiding image. So in this case, I'm using a pointing model in my mount. And really, this changes my life because now, once I've done this pointing model, I can point at any star and the monitor will go directly to it, and I will be able to detect immediately the star in the field of view of the guiding camera. Does it answer your question?
Yes. So my situation is your older situation, not so good. I mean, not so wonderful mount. So I will use a guide scope and like a guide CMOS camera behind it, and it's just enough. Or any should I match it with my telescope's field of view? Anything special there, or just camera?
In this case, you have to have a quite good alignment, but not a perfect one. In fact, for me, I used a very small camera, a very cheap CMOS camera, and a cheap lens. I think it was a 50 millimeter focal length or 70 or 80 millimeter focal length. It was enough to have few degrees in the sky, and few degrees is far enough to be sure that that there is no. It's very easy to align it with the telescope. It's a rough alignment, and then the problem is the first time you have to point at a star and to know which star you are pointing at, and then to control in the pointing image where it is to find to do the matching between the two images.
Okay. Thank you.
But you know, this is something, the first time it looks complex, but once you have done that 1 time, 2 times, 3 times, you say, oh, okay, easy. You know how big the movements of your telescopes are, and so you become familiar with the system.
Okay. Thank you.
Any other question or any other proposal, comment?
François, look at the chat. We have a message of Ron.
Would anyone like to see a laboratory that are modified? Oh, yes. Oh, so you mean you have okay? So Ron, you have added some motors to adjust the focus and to adjust also the rotation to the angle, the gratting angle, right? Do you have any picture?
Yes, can you hear me? I hope.
Yes, we
Oh,
can
great.
hear you
Okay.
and see you. Wonderful.
Great. Well, here, unfortunately, I had the brain aneurysm, and it stopped as soon as about when I finished this job. So this has not been on a telescope yet, but I have tested it, and it is working because my observatory is about 800 miles away near the Donald Observatory. So it's at a great site, but I can't go now because I can't go that high until I'm healed. But, oh, no, that's too much light.
Yeah.
I was going to show you how I took this design, which I think was just ingenious, and was able to take the design and, let me see.
Yeah.
You can see the 2 Hurst motors. There's a Hurst motor here and a Hurst motor here, vertical for the collimator, and using a tooth belt and a Hurst motor here to move the micrometer. Oops, there we go. So now the micrometer, when you want to do, say you want to look at your hydrogen alpha, that's fine. But if you have a Doppler shift that is not there where you want it, or you want to look at some H3 line, this was very inexpensive, probably, especially with the quality of this. You do have to have a good mount, and we use the American software, this Paramount. That's what I use, and it's very good for guiding, very, very accurate. And but I will say that coming back from my brain aneurysm has been very difficult. I had to retire my position as the director of the astronomy program at the university in Texas, and but I still join them. We have a spectrograph at Mauna Kea for 400 nights, and it's not as fun as this. This is much more enjoyable. We have been measuring making a catalog of the 400 most distant quasars, and their Doppler shifts. If you take the hydrogen alpha, it is so far in the infrared that it's almost impossible to see it. So we have to use other spectra to actually measure the distances and measure the content. And that's all paperwork, but I still love working with these. And after I got my Lisa, I started doing planetary nebula here just in this past few months. And it is wonderful. We caught an image of Abel 7, which is not in most books because they can't, it's so faint. But with the Lisa, you have time to make a long exposure and make groups of long exposures. And so we were able to also confirm, for example, that it was indeed a planetary nebula and not an H2 region. And so, I appreciate you guys that. And when we start from the beginning and go all the way to quasars from you, Oliver, it's how did you manage to do that in 2 hours? I could take 2 semesters and I can't get that far. So thank you.
And by the way, did you? Well, this is wonderful. Well, I love the modification that you made of the LARES3. And by the way, I told you that we're working on the motorization of the UVEX instrument, and this is something very close to what you are doing. And by the way, this is an important change in our world, is that more and more people are using their instruments remotely, and this really gives a comfort and efficiency and so on. So we are going towards remote observation. So this is a deep direction that we are going in. So congratulations for your change and all your observation. I just had a question. The Abel objects, I don't remember the number you observed. Have you put your measures in the Planetary Nebulae website?
I have to thank Oliver for telling me about it. I was not aware of that you Europeans had a site like this, because I haven't been keeping up. And when he described the site today, I wrote it down and I went to it. I went, oh my goodness, this is perfect, because I'm going to start looking for suspected objects, because even though you know, we still have the ability to use the largest spectrograph in the world in Mauna Kea.
Mm-hmm.
I still enjoy this more because, how can I say this? We're doing it ourselves, and we have time, and that's the thing we don't have. I mean, we may have a certain number of hours, but it's very, very expensive. And these planetary nebulae, they don't last. I mean, you know, they don't last a long time. So it's nice to kind of get the measurements before they fade away. And the LISA has been really pretty handy. I mean, we have a lot of time, and it's a good sky. And what we have to do is get we Americans are not nearly as far along as you Europeans are. I mean, everyone takes beautiful images, but there's no interpretation of those images. And that's what I appreciate what you guys are doing. And as an educator, that's what, I mean, it's wonderful. I mean, and I love what we're doing right here.
Mm-hmm.
So anyway, I give the floor back.
Thank you. Thank you, Juan. Any other question or comments? No, thank you. Well, in any case, if you want us, don't hesitate to send a mail to us, and we do our best to reply and to reply any question. And again, if you want to have any link to the community, how to participate to this program, or any question you have, don't hesitate to send us a mail, and it will be always a pleasure. Even if sometimes I'm not fast enough to reply to all the questions, but I really want to do it. Anyway, thank you very much. Thank you very much for your participation, and share this. Enjoy doing spectroscopy. Talk about what you are doing around you, and share your observation, and what we're doing together is just wonderful. Thank you very much. Bye-bye.
Bye-bye.
Goodbye.